Thank you so much, Janna, for such an interesting talk. And we do have a few questions coming in, but I do encourage everyone else to write them into the Q&A box at the bottom of your screen, and we'll try to make through as many as we can. But the first one comes from Ross, and I might butcher this word, but he asks, what's the difference between a quasar and a black hole?
A quasar and a black hole. So a quasar, quasars were originally discovered, they were called quasi-stellar objects because they kind of look like stars, but we couldn't tell if they were small objects nearby or big objects far away. And so there was a debate, and just again, in the spirit of discussing science, the most fun part of science is having a question you don't know the answer to. So this was one of those beautiful moments where the scientists of the time had a really meaty problem to try to grapple with. And we realized that quasars, which is the cute name that came out of the quasi-stellar object original nickname, are supermassive black holes. That is, black holes millions of times the mass of the sun up to billions or tens of billions of times the mass of the sun, very far away. So they were very powerful objects at a great distance. And that meant the fact that we could see them at such a great distance meant that they were incredibly energetic. So here you have this irony that the darkest object conceivable, the darkest phenomena conceivable, becomes the brightest beacon on the periphery of the observable universe. And so what's happening with quasars is that they're churning up magnetic fields around them. And it's very common. The Earth has a magnetic field. When you make a neutron star, which is a dead star that didn't quite become a black hole, it has an enormous magnetic field, trillions of times that of the Earth. And so these quasars have material around them that are carrying these magnetic fields, and the black hole is spinning, and what it's doing, it's creating a magnetic storm. And that's essentially what powers the quasar. So the quasar is powered by the black hole, but the light is not coming from inside the black hole, it's coming from around it. And it's coming from the mayhem induced by this spinning black hole. And so I would say quasars are simply one example of the mayhem and the havoc a black hole can wreak.
Thank you. The next question comes from Xavier. What are your thoughts about fuzzy holes? Do you feel this adequately solves the infinite point singularity challenge?
I'm not sure what you really mean by fuzzy holes. I mean, the expression didn't really take. I kind of remember people talking about fuzzy holes. If they could write to you a little more what they mean by fuzzy holes. But I'll talk about the singularity, which is a really good point. So when Penrose writes this paper in 1965, he says, not only does the star continue to collapse, leaving the event horizon behind, inevitably, it is forced to continue to fall until it creates mathematically predicted inevitably what we call a singularity, which is a region of infinite space-time curvature. And that means that as you approach, your little matter is also reacting and provoking that singularity and creating its own kind of storm. So singularities are bad things. They're bad not just because they're destructive and they would destroy you, but because, as Penrose noted in that paper right away, they don't really make physical or mathematical sense. They seem to predict infinities, which we've never really seen in nature. They predict that as your matter approaches a singularity, it just sort of falls out of existence. It just ceases to be. And that is anathema to physics, because it's as though you're saying there is no ability. And that goes against the entire paradigm of physicists. So most physicists, Penrose included, said, I don't really believe this prediction of general relativity. I believe that there will be a quantum phenomena that will protect us from the singularity. And so he says right away, singularities are predicted in Einstein's theory, and that probably means the theory is not complete, and that quantum mechanics will make it go away. He doesn't say how, and this continues to be, in these kinds of images that you're seeing here, something that modern physicists are struggling with.
Jamie asks, is there any chance of ever creating something like a black hole on Earth, even on a very small scale?
It's not impossible. So the Large Hadron Collider, which is in Switzerland, smashes particles together at such an energy that if you imagined a universe slightly modified, it's not inconceivable you would have made a black hole. Now, to do that, we really think that let me just think how high energy is a collider. So you would have to go 1,000,000 trillion times higher in energy, 1,000,000 trillion times higher in energy to make a black hole according to our standard understanding. And we're not going to reach 1,000,000 trillion times higher energy than the Large Hadron Collider. Now, the reason why some people thought, well, maybe we will make it with the energy that they're reaching in Switzerland was because if I manipulate space-time, if I imagine that there exist extra spatial dimensions, I can actually bring that energy down. It's a very subtle argument that I don't really have time to go into, but there were theories that, and these are real, actually quite solid and interesting theories, that there are extra spatial dimensions that we just don't notice. The problem is that the dimensions would have to be kind of big to bring the energies down, and we don't see evidence of that. And so it's all kind of colluded to suggest that, in fact, we would have to go to much higher energies. But some people were nervous enough about the idea that we would make black holes that somebody filed for an injunction against turning the Large Hadron Collider on. And there were some lawsuits that they were afraid that this experiment was going to destroy the Earth. Now, one of the arguments physicists made that, well, it's not going to eat up the Earth is because of Hawking's observation that black holes evaporate. And at that tiny scale, they evaporate really quickly. So that even if you made one at the Large Hadron Collider, it would be like a firecracker. It would just explode, and harmlessly so. And it would not destroy the Earth, was the argument.
Richard asks, how does entanglement square with a maximum speed for light?
Well, that's a very good question, because it doesn't. There's a famous paradox called the Einstein-Podolsky-Rosen paradox, where they showed that quantum mechanics violates the respect for the speed of light that we want. Right. So the idea is I take two particles that are quantum entangled, just meaning that they make a neutral pair in some sense. If one is positively charged, the other is negatively charged, they make this nice neutral pair. They exist in a state of quantum entanglement, which means you don't know which one's which. They're kind of in this nether world of the particles don't actually have firm concrete existence. We could go into an entire lecture about the Heisenberg uncertainty principle, which allows for that. But the idea was like, I put one in my pocket. It's like a chicken bone experiment is what I liken it to in the book. Like, imagine you crack a chicken bone at the kitchen table, but you don't look at the result. One of you puts a piece in your pocket, the other one puts a piece in your pocket. You travel to remote parts of the galaxy, and you look at your piece and you say, oh, I've got the big piece here, for my friend has a small piece. Okay, that's fine. There's no information traveling faster than the speed of light. In the quantum version, when you crack the chicken bone, those two pieces exist simultaneously in a state where you have the small piece, your friend has the big piece, and simultaneously you have the probability of the big piece and they have the probability of the small piece. It hasn't assumed a state yet. And that's quantum entanglement. Now you put gingerly your quantum piece in your pocket. It has not assumed whether it is the big piece or the small piece yet. And you travel to Andromeda. Now you perform this clumsy experiment, which forces your chicken bone to assume a definite state. And you find out you have the big shard of this game. And you know faster than the speed of light, and it has happened faster than the speed of light, that your friend has the small piece. Now, Einstein proposed this to point to the absurdity of quantum mechanics, which he always railed against. And he said, look, this is a violation of relativity. This can't be. Yet when experiments were performed, it is exactly how it is. And so quantum mechanics is in violation of relativity. And that's why people talk about the difficulty of understanding a quantum theory, not just of relativity, but of gravity, full curved space-time, not just of space-time, is because they don't play well together. And so this is a real opportunity for physicists. I said scientists love nothing more than a problem. This is a real problem that has been around for 100 years, nearly. As we approach the 30s of this century, it'll be approaching 100 years that we have not been able to resolve that conflict. But we know that the clues to moving beyond our current understanding lie precisely in understanding things like the quantum entanglement around black holes, that's the terrain in which we're doing our exploration.
David asks, can you please talk a little more about the implications of black holes on what is real and not real?
Yeah, well, so like we were just describing, after Heisenberg, so after the early theorists of the last century, of the 20th century, we started to realize that things we thought were real weren't really real. So if I think about a particle, like a subatomic particle, as real, with quantum mechanics, I begin to realize it's not always there. And that's a really difficult concept. If we look at the way, something really basic, like how an electron occupies an atom, the electron isn't in a precise location at a precise time. There's just this probability of finding the electron if you go and look for it. But it defies all desires to make it like a billiard ball that's really there. And an electron can appear on one side of an atom, on the other side of an atom, but it never ever travels in between. And so it really challenges our idea of what's real. And we've been forced to accept that at the quantum level, particles aren't as real as we previously thought. Now, black holes are really important to this description because black holes are also like fundamental particles in the way that electrons are, meaning it doesn't matter how I formed it, from the death state of a star or in the Big Bang or in an accelerator. Black holes are perfect and idealized in the same way that an electron is. And that means that it behaves in some sense like a subatomic particle. And so the reality of the black hole is something we grapple with. In this painting, this is depicting the idea that these quantum wormholes could entangle the inside of a black hole and the outside of a black hole. And if you imagine a kind of embroidery, let's say I embroidered an image of a black hole, from a distance you would think, oh, that's this object, it's this black sphere. But as you got closer, you would realize, oh, it only emerges from the overlapping threads, and it's not actually a solid object. And there is some thinking about that surrounding the idea of a black hole right now, that it emerges from these overlapping threads, which are the quantum wormholes, but on closer inspection, that's what creates the black hole, that the black hole isn't actually independently real outside of these quantum entangled wormholes. Now, it takes me like 3 chapters to get there, so appreciate the brevity of this response, but yes, we genuinely wonder whether or not black holes are real, or anything is real at this stage.
From Shay.
I think
from the pictures we see on your screen, black holes look 2D and flat. If they are larger inside, why do we not see multiple entry points to a black hole? Why do we not see them as a cylinder or rectangle shape instead?
Yeah, so mathematically, which is not a surprise, we find that black holes are spheres. After all, how would you decide where to put a corner? Like why? Because the black hole seems to be the same in all directions, the only possible shape for it in some sense is a sphere. If the black hole is spinning, there's a direction which is the spin axis, and that can make it a little more oblate. But basically, they are 3-dimensional. They look flat because how do you represent a 3-dimensional shadow? It's, the only way to show you that it's not flat like a disk is to travel around the black hole and take pictures from each side and build a composite digital image. And we do know that the event horizon for a non-spinning black hole is spherical. So there are entry points at every angle around the black hole. You would be crossing the event horizon. It absolutely is not flat. And that flatness is simply an illusion because it's hard to realize that there's a 3-dimensional shadow, right? You have to move around it and see it from all the angles to notice. So we definitely do think of black holes as 3-dimensional objects. Now, the profound question of how can I have a sphere which is bigger on the inside than the sphere suggests? That's one of the tricks of space-time. And here's an example. Imagine a flugelhorn. Do you remember those are like old-fashioned record players that have those big horns that fan out. If you were to try to judge from the perimeter of that horn how much surface you have inside and pretended it was flat, it would be a much smaller area than if you allow it to be a curved in this third dimension, in which case you can have this long horn with lots of surface area. And so it's harder to visualize when we're talking about a three-dimensional boundary, and interior volume is harder to visualize, but the concept is the same. The warping in space-time allows you to have more space on the inside than you would imagine just by looking at the perimeter. And I feel like maybe one more. Do we have time for one more, or are we?
Yeah, I think we have time for one more question. So Ross asks, what did Hawking mean when he said the area of an event horizon is larger than the total mass of the black hole?
So it's a beautiful thing, beautiful fact that when you measure the surface area of a black hole, it grows like the square of the mass. And so what do I mean by that? If you have a solar mass black hole and the area is 6 kilometers square, proportional to that. If you have a black hole 10 times the mass of the sun, the area goes up by 100. And if you have 100, it goes up by 10,000. So it grows as the mass in that way. So what Hawking, it was actually, the mathematics of it isn't so relevant. What's really profound about that is Hawking realized that the area of the black hole was what was most important to understanding how hot it would be, how much entropy it had. So in other words, how much heat essentially it gives off. What matters is the area and not the volume. And that's really profound. If you just let me jump back, let me see if I can do this quickly. That's really profound because, oops, sorry, that what that means is that there's this sort of restriction that depends on the area and not the volume. It's something like a hologram. So if you think of how a hologram works, what you do with a hologram is you take a like flat surface and you encode information on this flat surface. Now that's it. That's all you got is a flat surface. That's as much information you can pack as what you can pack on that surface. And it creates the illusion of a three-dimensional object. What Hawking led to, he didn't directly say this, this was said by people after him, but if I pack all the information I can possibly pack on a black hole has to be on the boundary, because the inside doesn't matter, because the event horizon doesn't allow us to know anything about the inside. So it doesn't matter how big it is on the inside. It doesn't matter what's going on the inside. None of that can matter because we can never know about it because the event horizon forbids transmission from the interior. So it's like a hologram in that all you can do is pack information on the outside, the surface of the black hole. And that's led to this entire area of research where people are investigating, maybe all that matters are these two-dimensional things that create the illusion of three-dimensional objects. And if that's the case for a black hole, it has to be the case for everything in the universe, that we're all really two-dimensional. And we're holographic projections that have the illusion of being three-dimensional. Because if I tried to pack more information, I'd simply create a black hole. And we know how much information a black hole can take since Hawking, which is only what you can pack on the event horizon. I know these are very abstract, difficult concepts. I'm not really expecting people to totally walk away with it, but the walk away should be, are we really two-dimensional beings in a two-dimensional universe with the illusion of being three-dimensional?
Well, thank you so much, Janna, for joining us tonight and for this fascinating talk. Thank you, everyone who joined us from home. I hope you enjoyed it as much as I did. And Janna's new book is out. And with that, I hope you all have a great rest of your day, your evening, wherever you're joining us from.
Thank you. Great to see everyone. Bye.